A very good morning to everyone. My name is Nikunj and I'm from MTech IT second year. And my roll number is IT2K2456. My enrollment number is D2402199. So here we will be solving internal 2 paper of our NAD subject. Here are 5 questions in this paper. Question number 1 is Newton's forward difference interpolation, in which we have to find the population at a particular given year. And question number 2 is 2D Lagrange interpolation. We have to find this point from the table. In question number 3, we have to do numerical integration using Simpson's rule. In question number 4, we use Gauss-Legendre quadrature formula to integrate this function. In question number 5, we use Newton's forward difference to complete the flow chart. So, Newton's forward interpolation. Topic: estimate. Question number 1, we have to estimate the population of city at 1925 and 1975, 1984. Its real world context: census data is collected every 10 years. Planners need estimate for intermediate 10 years for resource allocation. Method: Newton's forward difference interpolation. Best when x values are equally spaced and we interpolate near the start of the table. Formula is fx is equals to fx naught plus s dot delta f0 plus s into s minus 1 divides 2 factorial multiplied by delta square f naught plus s into s minus 1 into s minus 2 dividing s 3 factorial and delta cube f naught. So where s is equals to x minus x naught divides height of the given x. So the given forward difference table, the given table x and y are this, and we'll make the forward difference table. Delta 1 we'll get by subtracting 35 from 42, we'll get 7. From subtracting 42 from 58, we'll get 16. Subtracting 58 from 84, we'll get 26. Subtracting 84 from 120, we'll get 36, and this so on. We'll get delta 1, delta 2, delta 3, delta 4, delta 5, delta 6. Here x naught is 921, h is equals to 10, delta f1 is equals to 7, delta 2 f0 is equals to 9, delta 3 f0 is equals to 1, delta 4 is equals to minus 1, delta 5 is equals to 0, delta 6 is equals to minus, delta is equals to 3. So we have to find the population in year 1925. But we only have the population in 1921 and 1931. We'll take x naught is equals to 1921, which is known value. We'll take x, which is unknown value, which is given 1925. Height is 10, and to find s, we'll subtract 1925 minus 1921 divides 10. We'll get 0.4, which is s is equals to 0.4. So we'll getting the values which we need for Newton's forward formula. Fx naught is equals to 35. S dot delta 1 f naught is equals to 2.8 s into s minus 1 divides 2 factorial multiplied by delta square f naught equals to minus 1.08 and so on. So we'll omit the higher order terms, and adding all these values 35 minus 1.08, 0.064, 0.0416 will get the population in 1925, which is 36.83, and it is in thousands, so 36.83 thousands. So another part of the question is to find value at 1975. For 1975, we'll use x naught is equals to 1921 and s is equals to 1975 minus 1921, which is equals to 5.4. So the term fx0 becomes 35, the second term becomes 5, the second term becomes 37.8, the third term becomes 1.06.92, fourth term becomes 22.40, fifth term becomes minus 9.137, and adding all these values will get population at 1975. So the population during the year 1975 was 193.1 thousand. For 1984, we'll find S, which is equals to 6.3. The terms become 35.000, 44.1, 150.4. So adding all this value will get the population in year 1984, which is 258,000. Error in Newton's forward interpolation, truncation error. If you use terms up to delta n, error is equals to h to the power n plus 1 divides n plus 1 factorial. For 1925, s is equals to 0.4 near x naught. Low order terms dominate, error is small. In 1975, x is equals to 5.4, which is far from x0. Many terms need higher order differences group, it gives larger error. In 1984, s is equals to 6.3 beyond last tabulated value. This is extrapolation. Unreliable error is largest in this method. So this is the population and year graph, which is this. In 1921, tabulated is 35,000 value, status known. In 1925, interpolated value we got 36.83. In 1975, we got interpolated value 193.1. In 1984, we got 258,000 extrapolated value. So question one's conclusion was method Newton forward difference interpolation is ideal for equally spaced data when estimating values near the beginning of the table. In 1925, the value we got 36.83 thousand. In 1975, we got 193.1 thousand. In 1984, the value was 258,000, which is generally a low confidence because it is extrapolation. Error lesson, error grows with S. Larger the S, higher the error. Introduction to 2D Lagrange interpolation. Topic: given a 5x table of x and y and we have to find f 2.5, comma 3.5. Method will apply Lagrange formula. Given data table is this. We have to find f 2.5, comma 3.5. Target is this. So we use x nodes 2, 3, 4 and y nodes 3, 4 nearest neighbors. Lagrange basis, we will find the Lagrange basis L2 at 2.5, which is equals to 0.375, L3 at 2.5, which is equals to 0.750, L4 which is 2.5, L4 at 2.5, which is equals to minus 0.125. All of if we add all 2, 3, 4, we'll get 1. So yeah, it is correct. Step 1, interpolate x along x 2.5 for each row, y is equals to 3 and 4 using L2, L3 and L4 computed on the previous slide. Yeah, in row x we'll get f2, y 51, row y f3, 3 equals to 61, f4, 3 is equals to 66. Adding all this by multiplying L2, L3 and L4, we get 56.625, and if we keep y is equals to 4, we get value 40.375. And in step 2, interpolate. So step 2 will be interpolate along y is equals to 3.5 using y nodes 3, 4 linear 2 points. L3 becomes 0.5, L4 becomes 0.5. We adding L3 and L4 we get 1, so this is correct. After that we'll multiply L3 into f 2.5 and 3 plus L4 into f 2.5, 4. Multiplying and adding these values we get our desired point 48.50. So yeah, the value of f 2.5, 3.5 is equals to 48.50. So question number 2 is generalized 2D Lagrange algorithm. Step 1, choose q plus 1 x nodes x1, x0 and to the x cube. Choose p plus 1 at y nodes y0, y1 at yp. For each y node yj, compute Lagrange interpolation along x according to formula Lix is equals to pi whole bracket x minus xk dividing xi minus xk, interpolate gy along y using the computed gy values by the formula m1y mjy pi bracket में y minus yk divides yj minus yk. For quadratic, use three nodes in each direction. Error analysis. Interpolation in error 2D depends on smoothness of f and distance from the data nodes. Using more nodes reduce error but risk oscillation. Error analysis and conclusion. Method used quadratic in X 3 nodes 2 3 4. Error in X interpolation h cube since 3 nodes used. Error in Y interpolation h square since 2 nodes used. Overall error order hx cube dot hy square. Acceptable for smooth function. Risk f2 2 comma f at 2 comma 2 is equals to 16 appears anomalous and may cause distortion. Conclusion, f at 2.5 and 3.5 equals to 48.5 using linear 2D Lagrange interpolation. Question number 3, Simpson's rule integration. Integrating a function using Simpson's 1 by 3 rule. Given data and simple rule application, given data is x and y. This is segment 1, x is equals to 0.620. Will apply Simpson's on pair of individual intervals. Points are this. Height is 0.01. Will add in the first part, we'll add this 0.620, and then in the second part we'll add 0.022. In the integration of I1 equals to h by 3 multiplied by f0 plus 4f1 plus 2f2 plus 4f3 plus 2f4 plus 4f5 plus f6. I1 becomes 1.73 and I2 we use the formula same but with different segment. 1 by 3 into 2 plus 4 into 3 plus 5. Total integral is I1 plus I2, which we get 8.067. Error analysis, trapezoidal's rule, error order is h square. Simpson's rule, error order is h to the power 4. Simpson's 3 by 8 rule gives error 3h to the power 4. And graphical discussion, fx oscillates, values go from 4 to 384 minus 2 to in 0.620. Function is not smooth. Higher order methods may not help much. Large spike. Segment 2, steady 2358 parabolic fit is appropriate here. Unequal spacing between segments means composite Simpson must be applied separately. It is far better than trapezoidal. Question number 4, Gauss-Legendre quadrature. Integrate this function using Gauss-Legendre formula. Here we have n is equals to 4 Gauss-Legendre nodes and weights. We got the weights. These are the 4 weights. These are the t standard. And we'll calculate x using t. This is the x. And we'll put x in the equation. We'll get weight 1 into f. And then we'll multiply the fxi into weight and add all these values to get our integral 18.037 and putting it in the formula for integral b minus a divides by 2, which is the upper limit minus lower limit divided by 2 into the sum we get by multiplying weight into the f at xi. We'll be getting 54.11 exact value for verification. We'll integrate it normally. So yeah, it gives us 42. Comparative analysis and conclusion. Trapezoidal gives 38, Simpsons gives 41.5, Gauss-Legendre at n is equals to 3 gives 41.9, Gauss-Legendre at n is equals to 4 gives 42, and exact, which is analytical, gives 42. So error is less in Gauss-Legendre method. Newton's forward difference, introduction and formula. Write a complete flowchart for Newton's forward difference interpolation formula. This is our question number 5. The flowchart is, we'll be starting the flowchart and taking input n, x naught, h, x values and f values, building forward difference table, delta which is equals to delta fi equals to fi plus 1 minus fi for all I, and then this will complete the full forward difference table. We'll compute the S, which is equals to x minus x naught divides h. We'll set the result is equals to f0, term is equals to 1, k is equals to 1. If k is less than n, term is equals to term into s minus k plus 1 divides k. Result is equals to result plus term into delta k f naught, and we'll increase the value of k plus 1, and loop back. We'll do start iterate again, and we'll print the fx is equals to our result, and we'll stop the loop. Error analysis and conclusion. First term truncated at delta 1, second term truncated at delta 2, third at delta 3, which is cubic. Cubic is good for most practical token with other comparison with other interpolation methods. Newton's forward method is used when spacing is equal. Newton's backward is also used when equation is equal. Lagrange can be used at any equation. Complete paper summary is this. In question number 1, we used Newton forward difference. In question number 2, Lagrange. In question number 3, Simpson's 1 by 3 rules. In question number 4, Gauss legendary. Question number 5, Newton's forward difference. So thank you. I hope you guys will have understood the whole solution of the paper.